This is part 3 of developing an Ornithopter, which is something that flies by flapping its wings. I've already built 2 versions, neither of which actually flew. The last version looked like it really wanted to fly, but it's very hard to get the motor speed just right, and as soon as it was airborne the motor stalled due to lack of power, causing it to crash into the ground. I had to run the motor much slower than its top speed though, which means there's more power to be had if we can run it faster and use a higher reduction ratio before we drive the wings. The motor is a brushless drone motor and I already have the lowest kV rating I can find for its physical size, which is 930 kV. I'm using a standard drone ESC to drive it, which uses back EMF from the motor coils so it can work out the motor position and drive the phases at the right time. However, if the motor stalls it gets confused and so we lose power. This is fine for a drone where the motor spins near the motor's top speed without much resistance, so I'm hoping that if we can drive the motor faster and provide more reduction, and therefore more torque to the wings, we'll see less of an issue. I'm currently using a 2-stage belt reduction between the motor and levers that drive the wings. I considered a 3rd stage, but this would make the whole thing longer and offset the motor mass further backwards. It's currently really easy to tension the belt by sliding the mechanical sections away from each other and gluing them in place, and belts are a really simple solution with no small gear teeth to break. So I decided that I'd just increase the ratio of the existing mechanism by increasing the teeth on the big pulleys. I previously had 2 4:1 reductions which gave me 16:1 overall. I'm now moving up to 2 6:1 reductions which gives me 36:1 overall, which is over twice the reduction and twice the torque. It also means that the motor can run twice as fast, so hopefully the ESC will be happier driving it. Just a quick ad from my 3D printing sponsor. Thanks to LolsBot for supporting my channel with 3D printers. Thanks to 3D Fuel for the filament for this project and lots of other projects, so check out my channel for more 3D printing projects and check out 3dfuel.com. The mechanism is really similar to before, only slightly longer with these bigger pulleys. So we've got the main output shaft that drives the wings mounted on 2 bearings, and that fits into a section which rotates into place and then screws in to hold it nice and securely. The motor again is mounted on this piece, and I've got a bearing on the other end of the pulley as well as the motor bearing so that I can brace that belt and keep it nice and tight. And the middle section just slides into place to tension the belt, and everything's glued onto that carbon fibre rod so it runs nice and smoothly. Having those 2 reduction stages means that the belt ends up in the right place to drive the pulley on the end of the motor shaft, and that's the only way really to keep that pulley small enough to keep our reduction ratio. I'm using a standard RC set to drive this with the same ESC and the radio control receiver and a 3-cell LiPo. That seems to be running pretty smoothly. There seems to be quite a lot of power there and I can't stop that by holding it, at least not without getting friction burns. So I'm pretty sure we're going to have enough torque here, and at this point the motor's running top speed. I'm using the same wings off version 2 because they seem to be perfectly good, and this is airtight fabric glued onto some carbon fibre rods with some extra bracing. So basically this is the kind of structure I came up with after looking at other Ornithopters, specifically this one which has exactly the same wing configuration and it flies really well. And this one actually looks pretty substantial. It's smaller than mine, but it's got metal parts in it, although most of it's carbon fibre, and a pretty substantially sized battery. I fitted my wing levers to the structure and added some extra blocks there so I can get the holes in just the right place to get roughly 30 degrees of movement, which I've read is the right amount. And that seems to work perfectly well. So you can definitely feel the backdraft coming back, which is going to push it along. And the wings seem to hold up and the mechanism seems to hold up. All of the other components are fitted, including the battery, the ESC and the radio control receiver. And it seems to be slightly nose heavy, which is generally good for radio controlled aeroplanes and things like that, but I guess we'll just have to take it outside and try it. And I've put the same tail on from version 2, which is sloped up slightly, so basically that makes it fly up, and currently I've got no steering. So it's slightly better, you can see the motor isn't stalling, but ultimately there's still a few issues. So something came unglued there and I had to glue it to rebrace the belt. There's quite a lot of forces, but I was still not really flying any better than before. It turned out that the motor had popped out of its bearing and something weird had happened, so there's quite a lot of high forces on these belts. I've made a new motor mount and braced it with zip ties and also made the plastic a bit more substantial, so hopefully we can hold belt tension. But before we carry on with that, it's time for a quick ad from the video's sponsor, which is Mel Science. Mel Science is a subscription service that offers monthly science boxes which combine hands-on experiments with VR and AR technologies to engage kids in studying science. Mel Science are breaking the stereotype that science is boring, difficult, or only for certain types of people. The aim is to make serious science accessible, interesting and cool. Science is about exploration, experiments, discovery, and asking questions, all of which comes naturally to children. Mel Science boxes help nurture children's natural interest in science by giving them fun hands-on experiments to engage them, and serious detailed explanations to learn, as well as VR and AR technologies to dive deeper. The kits are presented well and are really good quality. I really enjoyed some of the optical experiments which cover lenses and polarised light. Check out the link in the video description and use promo code JAMES50 for 50% off your first box of the Mel Kids chemistry and physics subscriptions. So we get the odd good throw out of it. Sometimes it mainly nosedives or something else weird happens. That was a pretty good one, but it doesn't look like it's going to keep flying. I mean, ultimately it's diving, maybe picking up some altitude and then crashing anyway. I found this website called Ornithopter.org, which has got lots of useful information on, and it talks about the wings and how they actually give lift, because the downstroke and upstroke are at different angles rather than the upstroke just pushing the machine down again. It also talks about the wing bracing that we've got on the Ornithopter, and it mentions that that should be slightly flexible so that we can still bend the wing up and down as the front edge of the wing moves. Mine are made of the same type of rods on both of the braces, so let's take a look at that. I found this Ornithopter on Amazon called a Go-Go bird, which looks pretty cool. It's very small and very lightweight. It's radio controlled, so it flaps its wings. You can drive it up and down by basically giving it more throttle, and you can steer side and side with this little tail rotor, which is quite cool. It has actually got 4 wings, but you can see they're just a plastic cellophane material, so as the wing moves down, the wing material will bellow upwards and cause an aerofoil, and of course that won't happen on the other motion. It also hangs in the air due to its tail pointing slightly nose up, which pushes air backwards, and I guess that gives it lift as well. Both the front edge of my wing and that diagonal cross brace are roughly 4mm carbon fibre rods, so there is some flexibility, but not that much. So I decided to take a radical move here and just actually cut the cross brace up into lots of sections, so it's much more flexible. Now we can see that the whole wing is flexible, and as the wing moves up and down we get more of an aerofoil curve shape across the whole profile of the wing, even though the front edge is still pretty much staying in a straight line. So let's give that a go. And almost immediately we can see that flies much better. The battery's quite far back, which keeps it pointing upwards, although sometimes it seems to stall and then nosedive. So I try moving the battery forward a tiny amount just by sliding it forward, and sometimes if I throw it with enough force, it actually picks up and looks like it's going to fly out of my garden. So that looks like it's pretty successful for now. Obviously I've cut those rods up completely, so they now flex in all directions and they're all just in lots of rigid sections. So I decided a good thing to do would be to get some thinner 2mm carbon fibre rods and lay those alongside that, so we still get some flexibility but it still keeps some tension on the wing. So I've just glued those all the way along with super glue, which seems to be holding for now. But I think we're going to need a bigger test area. Well, it's flying better than it ever has before, although it seems to pull to the left a bit. I was hoping they would fly right over the camera, which is why I'm so far away. I got one really good throw out of it. Had it gone in a straight line, it would have been really good, but unfortunately it flew off out of shot, crashed, twisted the mechanism, and smashed everything to pieces. So I tried to make this light by leaving gaps in it, and I'd even put on some reinforcement because the parts had already cracked, but now it's completely broken through. I can still hear the belt skipping, so we're not getting full power, and that's because that little pulley doesn't engage with many teeth on the belt due to the much bigger pulley and the angle it comes in now, so we probably need to add some idlers. I actually cut the gussets open and glued the new carbon fibre rods inside with the old ones, although in doing so I've lost symmetry in the tension of the wings and I've got this weird wrinkle in one wing. This is the one that actually seems to give more lift and pushes it the other way, so that's another issue. Now I've Frankensteined the wings. So, of course, we're going to have to come back for another complete rebuild. I think really that wing tension and that wing flexibility is really unlocking the key to lift. So I'm really happy to have discovered that. And also I think I've got the right power to weight ratio, although I think we're still a bit on the heavy side. But having that gearing ratio, if I can stop the belt slipping, that seems to be the right thing here. And of course we could go to a faster motor, we could go to a 1400 kV or back to the 2000 if we just need a little bit more speed, although power of course will be constant because it's the same power rating of motor. So that's something else we can experiment with. I'm probably going to come back with another one of these and pretty much rebuild everything because multiple parts have broken. I've just noticed another thing has just cracked on the tail there. So all of the crashing really hasn't done much for it. So I'm going to make a much stronger structure that can hold those belts tight. A new set of wings which haven't been cut to pieces and multiply re-glued, and then we'll take it from there. If you'd like to support me through Patreon or YouTube channel membership, then patrons and YouTube channel members can get access to all the videos up to a week early and sneak peeks and pictures of what's coming up, so check those links out in the description to this video. Alright, that's all for now.